Hey everyone, in this video I'm going to go through questions 43 through 48 of the USNCO 2025 local exam. You can follow along with both the exam and the solutions document I've written in the description below. So let's start off with question 43. It's asking which atom among the answer choices has the smallest first ionization energy. And if you know your periodic trends, you know that first ionization energy increases in this pattern to the top right. So in terms of the smallest, from high to low, it will be like this. So let's identify the atoms in question. We have magnesium, aluminum, silicon, and phosphorus. So that's going to be these four. So since they're all in the same row, we expect that smallest first ionization is going to go left. So it would seem magnesium is our answer. However, this is an important exception to the trend, and the reason why is that aluminum has one electron in its 3p orbital. So unpaired electrons are already generally unstable, and if they're the only one in their subshell, that's like not going to be very stable, and it's going to want to lose that electron in order to become paired and not have a subshell for no reason. So it's going to be an exception, and aluminum is going to be our answer. And this emphasizes the importance of not blindly memorizing periodic trends and actually understanding why those are the cases, understanding the exceptions, and being able to apply that to real problems. Question 44. Uranium has 32 electrons with principal quantum number n equals 4, and the reason for that is n equals 4 just means 4s, 4p, 4d, 4f. So if you know where those are, that's just going to be this, 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 and this. And if you notice, uranium is all the way down here with an atomic number greater than 71. So essentially it's going to have all of the 4s, all the 4p, all the 4d, all the 4f electrons. If you count those all up, that's 32. I'm not going to do that here, but yeah, it's 32. Alright, question 45. So for this problem, you need to know some equations, or you could just know one equation and get away with it. So if you know the equation E equals HF, energy equals some constant times frequency, you already know that this is going to be A. But I'm going to quickly go through these. So from de Broglie's wavelength, it's going to be this. So yeah, P is the momentum, is going to equal H over lambda. That's not going to be true because it's proportional to 1 over lambda, not actually F. Velocity, it's a photon, so it's always going to be the speed of light. Wavelength is inversely proportional to frequency. You might know the wavelength times the frequency equals the velocities, and the velocity, in this case, that's c. Okay, let's move on to question 46. So question 46 is asking what information are we going to get from photoelectron spectroscopy. You can pretty much ignore the argon here. That's just an atom that they gave, or an element they gave, just for reference. But essentially, if you know what photoelectron spectroscopy is, you can easily answer this question. So I've put a graph of what a spectrum looks like here. This isn't argon, but it's just some other atom. But you can see essentially we have binding energy here and number of electrons here. In a more formal spectrum, I guess this would probably be relative number of electrons, but you know, you get the point here. Essentially, it tells you the binding energy, which is going to actually increase in this way. So the ones on the left side here, are going to be closer to the nucleus than the ones on the right side. So we've labeled the peaks here 1s, 2s, 2p, etc. And you can see how 2p is 3 times taller than 2s here, because it has there's 6 electrons in 2p compared to 2 in 2s. So essentially you can figure out the electron configuration from photoelectron spectroscopy. So if you can do that, you can figure out ionization energy as well, because remember, you're given this binding energy here. And you can also figure out electronic subcell structure, of course. That's what we have in the spectrum. So our answer is going to be C. All right, let's move on to question 47. So question 47 is saying, is asking which statements about fluorine are correct. And essentially, if you know periodic trends, you'll know that both the trend for electronegativity and ionization, or electron affinity, are both this way. Fluorine is at the topmost here without being an inert gas. So it seems that both are going to be correct. However, there's an important exception. So electronegativity is correct. However, electron affinity for fluorine is not the largest. In fact, chlorine has the largest electron affinity. And the reason for that is another exception. However, this one is probably less reasonable to, like, if you don't know it off the top of your head, it might be a little harder to reason out, but you can still do it. Essentially, fluorine has valence electrons in small 2p orbitals. So whenever you add an electron, there's going to be a lot of electron-electron repulsions. When you consider what electron affinity is, essentially those repulsions mean that the electron affinity decreases compared to another high placement in the trend position, chlorine, which has valence electrons in 3p, which has less electron repulsions because of a larger size. So in fact, II is not going to be true, so our answer is going to be A. So yeah. All right, now question 48. This is asking us to do some nuclear decay, so I'm just going to hop right to it. It's saying thorium-232. That's this right here. We have, so the 0th step, I guess, we have 90 protons. It's thorium-232. That means 232 is the number of protons plus neutrons. So doing some quick math, we get 90 protons, 142 neutrons, and then we just do our decay. So I'm just gonna quickly figure out what this is. We have an alpha, then a beta, then a second beta, and then a second alpha. So we're gonna have, for the alpha decay is the release of a helium-4 nucleus, or 2 protons and 2 neutrons. So we're going to subtract 2 from each of these numbers. And then we have a beta decay, and a beta decay for, in the context of USNCO, is going to be a neutron being converted into a proton. So we're going to add 1 to our proton thing, and we're going to subtract 1 from our neutron number. And that number is going to stay the same for this. Number 3, we have another beta decay. So again, we're going to do the same thing here. We have 90 protons and then 138 neutrons. And then we have a second alpha particle. Our final step of decay, we again subtract 2 from each number here. So we're going to end up getting this here. If we add these up together, well, actually, we don't need to do that. I'll explain why. We have proton number 88. That's going to correspond to radium. And the only answer towards the radium is going to be C. You don't need to add up the mass number, but if you did, you would get 224.